Hi, my name is Alex Fleischman, and welcome to the video overview for the mass spring pendulum demonstration. This demonstration will allow students to analyze the equation for period of a mass spring pendulum. Students will experimentally determine three values for period based upon a pendulum with three different mass heads. Teachers will subsequently introduce the equation for the period of a mass spring pendulum so students can calculate the spring constant of the spring used in the demonstration. Let's use the stopwatch to time the period of a mass spring pendulum. We can do this by timing how long it takes the pendulum to make 5 revolutions, up, or down, down, then divide that number by 5. So period is equal to the time to make n revolutions divided by n revolutions. Let's make a data table. You can make the same one in front of your classroom. Well, the mass heads of our experiment were 0.2 kilograms, 0.3 kilograms, and 0.4 kilograms. Now, a couple of my AP students were nice enough to find the period regarding each mass head. They found that it was 0.2, 0.24, and 0.28 seconds, respectively. So from this experimental data recorded, what can we conclude about the period of a simple pendulum? Well, the period of the pendulum is affected by the mass of the pendulum head. Now let's look at the equation for the period of a mass spring pendulum. Period is equal to 2 pi, the square root of mass over the spring constant. Period is affected by both mass and variable k. Variable k is known as the spring constant. Spring constant is a characteristic of springs that differ with every spring. Given this equation, we can now mathematically find the spring constant of our demonstrated spring. First, we divide both sides by 2 pi, then square each side, and then multiply both sides by 1 over m, and we get that k is equal to m times 2 pi squared over t squared, which is equal to 4 pi squared m over t squared. And when we plug in our values for mass and period, we get that the spring constant used in our demonstration is 200 kilograms per second squared. This slide is for the AP Physics 1 courses. When the spring is at a maximum, or all the way stretched, the kinetic energy is equal to 0 joules, and the elastic potential energy is at a maximum. This is because the mass has an instantaneous velocity of 0 meters per second at a maximum/minimum amplitude when the spring is all the way stretched. When the spring is all the way stretched, the displacement of the spring is at a maximum. Therefore, elastic potential energy is at a maximum, because elastic potential energy is equal to 1/2 kx squared. When the spring is passing through the equilibrium, or not stretched, the kinetic energy is at a maximum, and the elastic potential energy is 0 joules. This is because the mass is moving the fastest as it passes through the equilibrium point. Therefore, kinetic energy is at a maximum, because kinetic energy is 1/2 mv squared. The spring is minimally, or not, compressed when passing through the equilibrium point. Therefore, elastic potential energy is 0 joules, or at a minimum. So what have we concluded? We have concluded that the period of a mass spring pendulum is dependent on both mass of the hanging block and the spring constant of the spring. Also, the period equation for a mass spring pendulum is period is equal to 2 pi the square root of mass over the spring constant.